Suppose we have a vector function r of t that has components f of t, g of t, and h of t. Also can be expressed, instead of using angle brackets, using ijk notation, f of ti plus g of t j plus h of tk. Boy, that's a lot of letters running around. We're going to develop the concept of a derivative of the vector function. R prime of t is equal to, by definition, the limit as h approaches 0 of r of t plus h minus r of t divided by h. And you'll notice it's the same expression that we use for real functions, but what does this mean in a vector function context? Here I have a curve C in the xy plane, so we'll develop this in 2-space, although it applies to R3. And C is given by r of t. So here we have a vector r of t with its head as a point on C. And then we're going to draw another vector, r of some other value. Let's see. How about if we use t plus h? Yeah, I'm sure you saw that coming, right? We're going to form a third vector from the head of r of t to the head of r of t plus h. That third vector is r of t plus h minus r of t. And if we saw that in a previous video, but if you're not convinced about that, add r of t to r of t plus h minus r of t. R of t's cancel out. We end up with r of t plus h. Now, if we're thinking about h values that are really small, then we end up with a vector that's parallel to that green vector, and it's the vector r of t plus h minus r of t divided by h, right? Because a small denominator means we're going to scale that vector. It's going to get longer and longer. But folks, as h approaches 0, the head of r of t plus h is approaching the head of r of t, and the vector that we end up with is called a tangent vector. Here's the way I think of a tangent vector. Suppose this curve were a roller coaster. And as long as the roller coaster rails or everything's fine, then the car will just cruise along the curve and everything will be beautiful. But suppose that at this point, at the tip or the head of r of t, suppose the roller coaster's broken and the roller coaster flies off the tracks at that point. The tangent vector is the direction that the roller coaster would fly in. So this pink vector here is the derivative vector. As we saw in a previous section, the limit is taken for each component. So we can write it as dr dt, that's d vector r, is equal to r prime of t. And we have f prime of t, g prime of t, h prime of t as a vector. That's in angle brackets, and also, of course, we have f prime of t I plus, g prime of tj plus h prime of tk. I guess I got tired of all the letters and wrote the same one over and over. I think that's worth putting into a box. Speaking of boxes, we have properties of limits that are presented in the textbook, and they mostly say what you might expect, except there are some surprising things here. We've got u and v are vectors, and they're differentiable vector functions. C is a scalar, f is a real valued function. The sum of two vectors and taking their derivative is the same as the derivative of the sum. The constant multiple rule follows. The interesting things here, I think, are really 3 through 6. F times u, f being a scalar function and u being a vector function. That derivative, it's a form of the product rule, f prime times u plus f times u prime. There's also a product rule for vector multiplication. U and v here are being multiplied together by the dot product. And it's the same thing, the same looking format for the product rule, except it's a dot product each time there's a multiplication. So u prime dot v plus u dot v prime. Same thing with the cross product, where the cross product takes the place of the dot product. Finally, if we have a composition function, so u of f of t, then remember u takes in a real value. So f of t is a real valued function, right? Then we have the derivative of the outside function, u prime, times the derivative of the inside function, f prime. So the chain rule works the way you think it would. Adding functions together and multiplying by a constant work the way you think they would. And then we have these new expressions that involve vector functions and real functions as appropriate in various product rule forms. Now the first one is clearly a vector function because we are adding together two vector functions. I think it's clear that the second one is also a vector function because it's just a scalar times a vector function, right? The third one, we have a real function's derivative times a vector function, but the result's going to be a vector function as well. Skipping down to number 6 here, we have a scalar function times a vector function. Again, even though they're derivatives, the result's going to be a vector function. For number 4, though, we have a dot product. And remember, the dot product of two vectors that have numerical components is a scalar. Here we have a dot product of two functions, two vector functions, and so the result is going to be a real valued function, or a function that spits out a scalar. For the cross product, since it yields a vector, the product rule with the cross product will also yield a vector function. One more thing here before I call it quits on this video here. The tangent vector with length 1 is the unit tangent vector. And that vector is denoted with an uppercase T of t, and it is r prime of t divided by the magnitude of r prime of t. Remember, when you divide a vector by its magnitude, you get a vector whose length is 1. So the idea here is we had this pink vector here, which was the tangent vector, and t is a vector that is parallel to that vector, but has a length of 1. So I'll call that T of t there.